And today in the shop I have an electric Mistress. I know some of you wouldn't be that surprised, but it's not what you think. It's one of these. Well, this effects pedal was made in 1979 in New York by Electro Harmonics. There's 3 control knobs on the front. Some of them make sense. You've got rate, range. Not sure what they mean by colour. What does that do? There's 3 sockets on the rear. There's a guitar input, a direct output and a flanged output. This is the interesting one. At the heart of this early effects unit is a Bucket Brigade chip which literally passes the signal through a chain of hundreds of storage elements, causing a delay. Delayed signal is mixed with the raw signal to make all sorts of effects like flanging and echoes. And this technology replaced the old tape loop machines, but it's long obsolete itself as it got replaced by computer systems a long time ago. Well, we'll just turn it on. Well, I think that's on. There's no lights on it or anything. You can't tell if it's turned on. Let's plug some outputs on it. Well, we've got an output signal. It's not responding to the knobs or the matrix switch. That's why. This is the colour adjustment. Okay. Range is doing nothing. I'm not seeing any flanging effects. It should be like a smearing of this waveform, and it's not happening. Well, that's not a good sign. I was rather hoping it was going to be completely dead. That would be more repairable. Let's get the back off. The bottom cover's quite simple. Just a flat plate with 6 screws. I do love these old PCBs. They did the tape routing. This is lovely. All these curves. Very 70s. There's nothing to see visually, all looks pretty solid. But these knobs are going to have to come off. Let's get the board out. And here's the component side. I'm definitely not the first person in here. Well, not a surprise after this length of time. But it's probably like 43, 44 years old, this stuff. 1979 date codes. It's just got op amps in here. Oh, lovely. Self-destruct tantalum capacitors. I don't think they're shorted because it's working, sort of. And down here we got 2 chips in sockets, which suggests that they might be a bit more sensitive or they need changing a lot. This one here is a 4013 chip. This is pretty standard logic chip. This is actually a dual flip-flop, and this will be no doubt used to generate the clock signal for driving this Reticon chip, which is upside down. The SAD1024. This is the Bucket Brigade device. Long obsolete. If that's knackered, we got problems. It's always worth checking online for any schematics before you start a repair. It can save a lot of time. And I've struck gold. There aren't any official schematics I found, but Ralph Metzger's website, he actually reverse engineered these and provided all the schematics. This is really helpful. Cheers, Ralph. The power supply is nice and simple. It's just a 15 volt regulator. There's a diode there to provide this plus B, so there'll be a voltage drop there, so it'll be about 14 point something volts. This whole bottom half is the clock generator. It actually generates 2 different clock phases, which is important for the Bucket Brigade device. And the top half shows a signal path going from input all the way to output. It's quite easy to follow. You've got a bit of a buffer amplifier, a bit of tone control, and this is the delay device here. We'll soon be able to tell if this is faulty. If we've got signal here and nothing coming out here, that's bad news. So the input's on pin 2. There it is, and then we go 3, 4, 5, 6 for the output. Nothing. The other output is pin 12. Nothing there either. I'll check the clock signal on pin 3. This is why I have lots of oscilloscopes. Well, probe pin 8 is a bit easier to get to. If we adjust the rate pot, it's working exactly as we expect. Look at that. And this should be the flange depth. Oh, not working. The switch. You have to turn the switch on. There you are, doing its flanging. It's worth noticing that there is no change to the output of this at all. Hardly anything. Just discharge any static. Not that there's any in this country. Just lever this chip out. That wasn't what I planned to do. I've got the data sheet for this little chip, and there's an interesting thing to show you. it's actually got two identical sides. This is actually two delay devices in one chip. They're actually 512 elements each. And that's significant because they're only using one pair of outputs. So the outputs on the chip are pins 5, 6, 11 and 12. Well, let's bend them out and have a look. So we'll bend pin 5 out, and we'll do pin 6 as well. And that one. And that one. So there's your input signal. Wobbling around. So the outputs, dead. This one also dead. Oh God, this side. There's summit. That doesn't look like what it should do. And this side, yeah, not good either. The output should look like this. They should be sort of flat at different amplitudes. I'm expecting to see a bit of a blur on top of like this pedestal as I mentioned it. It's not what we're seeing. Well, that scrapped the idea of using the other side of the chip. Can't do that. It'd be very easy to replace these chips, but look at the price people are asking. $250 each. That is ridiculous. I have to see what's in stock though. Oh, and the cupboard is somewhat bare. These things here, they're a bit cheaper to buy, these units, but they're really nothing like the Reticon chips. Although they've got a lot of elements, like 4096, these will outperform it in terms of a delay time. So this is all there is left. So this is the datasheet for the newer SAD1024D. The clock input in this will run at 5 volts or TTL. The other one didn't. Furthermore, there's only one clock input. There's none of this two-phase stuff. Although it's 5 volts it will accept, it can go as high as the supply, which is 15 volts. So yeah, I think we can use this. Electrically it's good. I think it's time to do a bit of designing. This is the pin out for the SAD512 and I'll compare it to the schematics of the electric Mistress. Now, first thing to look at is the clock. Now the clock comes in on pins 8, 10, 3 and 14, so any of those will do. 8, 10, 3 or 14. We can see that ground is on several places. What's that? Pins 1, 4, 13, 16. We've got the two outputs here on 6 and 12, so we go 6 that one, 12 there. VBB is pin 9. The input is on 2 pins, 2 and 15, so we've got a choice of there. What am I doing? 2 or 15. As for the sync pin, there never was one on the old 1024. And it mentions it here somewhere. If the sync input is unused, connect it to ground. Okay. So that is also 1, 4, 13 or 16. Whoa. Now VDD went to 4 places, 5, 7, 9, 11. 5, 7, 9, 11. Now below this I've mapped out the pinouts on the Mistress's circuit board. My plan is to make a little board which plugs into this socket, or maybe replaces it, I'm not sure. But there's a bit of room on the left, bit on the right. Yeah, I'm thinking of putting the chip sort of straddling this round here, and I'm going to line pin 1 up with pin 3, so we'll have it there like this. So that's pin 1, 2, 3, 4, 5, 6, 7, 8. What's happened to this pin? I mentioned the clock input right next to number 3, that's an obvious one. We'll just link this here. Pin 3 it's got to go to pin 6. So pin 4 will have to go to this other output, so I'm thinking round here maybe. So pin 2 is ground, well, that's easy, straight there. Pin 5 goes to VDD, that's easy. Pin 6 is an input, so that'll have to go, maybe you can go like this. Pin 7 is sync, that's got to go to a ground. Pin 8 is going to go to VDD as well. Yeah, well, a bit awkward, but yeah, like that maybe. Oh, there. All there. All I need to do now is lay that out on a PCB. Now that's done, I've got this transparent print of a circuit board which can be etched. I've got a piece of pre-sensitised circuit board here. Let's peel the cover off, stick it somewhere else. Just put that on there, just like that, that'll do. That holds it flat. Put the light box on. Let's give it 4 minutes to go. Just put the board in the developer. Oh, it's a bit dark. Probably need to change this. Yeah, I reckon that's about good. Let's rinse that off. Just put a little bit of tape on the back just so I can pick it up out of the ferric chloride. Just like that. And just float it on the top. And leave it for a while. This looks done to me. Yeah, pretty good. Just rinse it off. Okay. I'm just going to check this for any shorts because some of the tracks are a bit close to the pads. Just looking for any major defects in this. There's a couple of little nicks missing out of it, but it's good enough. But it's this little track here. Right in the centre, it's very close to the pad, and the CAD package I couldn't quite get it to move properly, but I thought it was okay. Now this is something that you find out about PCB production, is the capability of the manufacturer. It's just how fine can they make these reliably. And you can see here it's not the cleanest of etch there, it's not brilliant. I don't think it's conductive, but it might pay just to run a sharp tool down there just to separate them. If I look at this other board that is also underneath, that's a better one. But you can definitely see there's a little connection there, a little bridge. I'm just going to try and clean that up with the knife. Just drag it down slowly. Yeah, you can see there's copper. Yeah, just separate that up. Yeah, that should do it. Handy little scope, that. Let's wash the rest of the photoresist off. Splash of acetone. That looks rather lovely. Now I need to make some chip legs which are flat for the socket, so I'm going to take a bit of this round wire and roll it. Don't know how much I need, say that much will do. Just feed it into the roller. Just bring that back round here. A bit more. So this flattened wire should now fit in this socket nicely, and it does. Beautiful. Just going to make 16 legs now. Bend the end over and snip it. Now that's some legs made. I'm just going to put some flux on here to make it a bit sticky and also give us a good solder joint. Might need these little tweezers now. My thoughts are just to poke the legs through there, point them the right way, then solder it. And another one. I'll put a few in. There was always a risk that would happen. And repeat for the other side. Plenty of flux, tweezers. It doesn't look bad first attempt. I just need to straighten these legs a bit. Just use a chip straightener. Go in there. There we go. Oh, beautiful. I'm actually going to fit this chip in a socket itself, because it being so rare and expensive, you know, it might be worth a fortune. I certainly don't want to give it any stress by soldering it if I don't need to. So I'll have to solder this from the top, so again, plenty of flux on there. Look at this, has got turn sockets, which is actually quite posh. It also means it stands off the board a little bit, giving me a chance to actually get the soldering iron underneath. But I'm going to need a smaller tip for this. Fuck. That was hot. I can try one of these chips. Brand new, they say. Well, the legs need straightening. That's the top end. Pin one goes here. Well, that should do it. Let's hope it fits. It should do. I put enough effort in. Yeah, it looks good. Well, it fits in nicely. Let's hope it works. Let's hope we got some sort of flange effects or something. Ooh. Nothing. Well, I'm not a happy boy. I've been scammed. They're all fakes, there's a lot of them. I'm really annoyed at this. Now this elaborate mess is actually pretty much what the data sheet says. Over this end I've got a clock signal generator, it's a two-phase clock. Then we got just a buffer amp for the input signal, because I've biased it into the sort of middle of the power supply. And this is just the output. Now I've got all the ratings for this device here. It runs on 5 volts but can go up to 9. And here's the pin out. So basically we've got ground on pin 1 and the power supply is on pin 5. Look at that, 9 milliamps, 1.25 volts. That thing's clamped the voltage. After a bit of testing stage by stage, I found out it does that with only the power supply connected, and to get around it you have to reverse it. You've got the wrong polarity. And now, look at that, 1 milliamp, more like it. And that's mainly being used by the clock circuit. Unfortunately there's no output. This green wave is actually the input signal and these are the outputs. They are literally sat at 0 volts. There's a bit of noise there off the clock, that's 20 kilohertz. I can increase that or decrease it. So it's making no difference. If I turn it off, just at ground potential. That chip is not working. This time we've got the SAD1024 in there, wired exactly as per the data sheet. Got the positive voltage there. Got a diode there just to drop the voltage down by about 0.7 volts just for the bias of the transistors. This is a sync pin tied to ground, exactly as it should be. This is our input signal, clock signal, ground. These are the outputs here. The drain supply voltage should be between 10 up to 17 volts maximum. Let's see what it does. We'll stick it on at 5 volts again. All happy there. If I turn the voltage up, it's supposed to be minimum of 10 volts. Look at that now. Current limit 10.39 volts. Doesn't matter what I do. This chip is in a breakdown condition there. Yeah, those yellow and blue traces are supposed to look like these. Supposed to be square waves. And they're not at all stepped like that. This thing isn't working. But this doesn't bode well for the electric Mistress, unless I throw more money at it. Well, after a fair bit of eBay nonsense, I've managed to get my hands on a real one. But it's properly packaged in the anti-static foam, and look at that. It's got the original sort of prints on there. This is looking very promising to me. On the left is a genuine one, on the right is a fake one. You can see the markings are nothing like, really. They might say the same thing, but yeah, laser etched on the right, ink marked on the left. If you have a look at the underneath of these, that's the new one, and this is the original old one. So now you've seen it. If you're buying any of these, you know what to look for. Don't buy the new fakes. It's all very well me getting excited about it being original. Does it work? Let's give it the proper 15 volts. It's happy at that. Most of that current's driving the other circuitry, I should imagine. And wonderful, look at that. That's exactly what it should look like. I'm going to slow that clock down and see if we can see exactly what's going on. Again, it's trigger on the clock, see if it looks a bit better. What you're seeing is the outputs of the buckets, the Bucket Brigade chip, varying with the level as the sine wave signal comes in and out. Perfect. Well, if you ever wonder where I'll get my happy pills from, moments like this. Well, I tracked this thing down on eBay and it turns out the seller subscribes to this channel. Cheers, Mark. But it's time to install the chip in the little socket in its rightful home. Moment of truth. Encouragingly, we've got output. Let's make some adjustments, get some flanging on stuff going on. Well, there's stuff happening on the oscilloscope, but you can't hear anything. It's very subtle. What is going on? It's still not doing it. We have to check the setup of this. Because we changed the chip, probably need to check the balance. We just click on this potentiometer here. Oh, it's moving around. Ah, that's because this switch is gone. Okay, so what we're looking at is the two outputs of the chip sort of mixed together. So these here, this is the signal levels, and they should be at the same point. So we can adjust this potentiometer so that they match all of the way. Yeah, about that. There we go. Well, I've modified the drawings now with my mod there. That's right, but what's important, this bias here, the voltage that the signal comes in should be ideally around 4 volts. And there's a little trimmer here to adjust it with. And the input comes from pin 1 of this chip here. So just probe onto that. So we've got 2 volts per division here, from here, so it's 2, 4, 6, nearly 8 volts this bias. So this waveform needs to come down about here. Okay, now it's working. Well, now it's basically working. I'm just going to change this capacitor just because it's a bit untidy. We've got a wire come off as well now. Well, actually this looks a bit weak. Yeah, let's remake the end of those. Let's concentrate on the job in hand. Change his cap. Yeah, it's 35 volt 220 microfarads. That's what it says. So I'll just bend that out of the way. I can get this cap in upright. There we go. Might as well put the pots back to the lid. Get it all lined up. That broken bit off there. Now I've got to tidy those cables up. This is a perfect chance to try some wire strippers. They've been sent to me by Mitch Gray in Oklahoma. And he sent me 2 ideal wire strippers. T-stripper wire strippers. Made in America. Good quality, I should think. Well, they certainly feel nice. And if I understand, we've got solid and stranded side here. So I'm thinking if I take the undamaged wire, I can use this to gauge what size it is. I can find the undamaged strands. Yeah, just trying these different holes, 16, 18, 20 gauge. Yeah, not doing 22. It's 20 gauge wire. So, in theory, I'd go to this green one, clean the end off. 20 gauge there. Oh, I'm impressed. These are very good. Oh yes. I'm genuinely really impressed with these. These are great, Mitch. Thank you. So there you go. I recommend these. Not happy with that one. That's better. Now the base can go back on. Both the holes will line up. I guess it's symmetrical. We'll screw in there. We can turn that off now. Too many scopes running in here, it's getting warm. Well, it sounds fixed to me anyway. So what have we learned today? Firstly, these wire strippers are brilliant. Secondly, the Andonstar Microscope still working really well. Links in the description. And finally, don't buy fake chips. It's never good. Catch you next time.